the last talk of this session. Yeah, Professor Edward Shuriak is online.
Yes.
And yeah, so please start. We have 45 minutes.
Yes.
Okay.
Thank you.
Thank you.
So this is the title of this talk. There are many things to discuss. I was trying to be daring and select topics which would be, I hope, interesting to Vikash. And we'll speak about a little bit about general what happened in the last 40 years, and then focus on sound and sounds and their intelligence and the deep mind. So I start with the first time I came to India. That was the first PGP meeting organized by Vikash. And I should say that was an unforgettable experience. First of all, it was the first visit to India. At that time, I was in Novosibirsk, which happened to be nearly the same time zone and nearly the same temperature to the sun. So it was minus 20 and 20 just after this flight. Now, it was also on this first KGP meeting, I gave very much attention because I was the first speaker, happened to be the first speaker, and there was TV interview, this venue there with these huge bouquets of flowers, and India in all its millions of colors. But the most important, of course, was that we get a lot of new friends, full of enthusiasm. That it was this picture of Vikash full of enthusiasm as a young person here to go and to study, which at that time was just the beginning. That was before Riga LHC. So the meeting was very successful, and let me tell you one proof of it. So after the conference, our delegation, which consisted of Zinoviev, Tevyakan, and myself, unfortunately I'm the only one alive, can tell whatever. So we just fly from Mumbai, as it was then called, to Delhi. We were supposed to spend the day there, so we went to hotel. We take rickshaw on to take us to the hotel, and rickshaw on the way asked where we come from. We say we come from Bombay. He said, you're probably from Plaza Conference. So randomly selected rickshaw, hundreds of kilometers away from we knows about it. That was really something. So here is my outline. I go a little bit into history, show a little bit the flows, then treat them as sounds, and you'll see how that goes. We also learned in the last years that even small systems, as we call it, for example, PA and in very high molecularity PP shows hydrodynamical explosive behavior. I will skip this part because it is very well known. And then I will move to QCT phase transition in cosmology and focus on the sounds and ask what happened with these sounds. You see, if sound get to infrared, become large wavelength or small k, its damping is proportional to k squared, so it becomes very long-lived. And what happened with the sounds, and whether the sounds can be in principle observable, say that some years ago I wrote kind of a review about this, including this kind of dynamics. But of course, there is a lot of activity, especially on these early stages, which John and Paul was just speaking. Okay, so let's go to the beginning. When I fresh start thinking about final temperature QCD, and the first thing which was found was that if you calculate polarization operator, this is diagrams, and the dots means Coulomb field longitudinal, and the dash are transverse gluons. So in this Coulomb gauge calculation, it is this funny diagram B, which did contribution -6, and that is basically freedom. This minus is totally freedom. The reason why this diagram can get minus coefficient of logarithm is because it does not have imaginary part. And because transverse gluon and Coulomb gluon are in physical states. So that was known by that time, and the question is what happened in final temperature. Is it screening or anti-screening? So it turned out that when you calculate screening mass, this diagram does not give any contribution whatsoever, and all others are positive as necessary, so quark-gluon plasma become plasma because of screening. The other thing was that the magnetic screening is absent in perturbation theory, while we do know that we have it and we see it on the lattice. That started a discussion of monopoles, and this is another big story which I will not go now. So then in the 80s, we were inventing the signals, waiting for ligars to come on, and one of them was the nucleated probes, which I already mentioned. Also, Vikash and his team were working on this a lot. I will not speak about it here. The second one was a robust hydrodynamical explosion, and first we thought about radial flow, then elliptic flow, and then higher harmonics came up. Of course, there is jet quenching, there is germanium, plutonium, and many other things. Here is the slide which you have seen many times. This is from summary a few years after Rick started. And what you see here on this upper block are elliptic flow V2 over simplicity by epsilon 2 as a function of Pt. And here are some calculations. There's red lines here. Here, protons and pions are our initial hydra with Derek-Tini, and you see it very accurately predicted. That was done before the data, and it very nicely predicted the elliptic flow. The main phenomenon is that V2 grows with Pt, and that is the result due to this splash, very large radial flow. And all the people who try to use cascades and Parton cascades, etc., instead of hydra, have very big difficulty to reproduce this growing feature. It was growing a little bit and then become constant, so that because V2 has geometrical, not hydrodynamical origin, or in other words, the radial flow was not robust enough. Now notice that our curve stopped somewhere around 1.7 GeV. We didn't have the courage to calculate further. We thought somewhere around 1 GeV hydra stops, but no, it continues. And now we know it goes further, and this is an interesting thing. The question is when it stops. So here I present some discussion of this. Normally, hydrodynamical calculations are presented out to Pt about 2 or 3 GeV, where there is a maximum, and then epsilon will start going down, etc. What happened in a spectrum? example, in the ion kit is at large enough transverse momentum, as you know, spectrum become power lines. So this is power line tail due to jets and things like that. But it really appears visible. You can also see it in other particles, of course. It appears for ion at PT around 4 GeV. This is very large transverse activity of ions. And the question is whether we understand how ions can get there. So, or in other language, can we use hydrodynamics all the way to 4 GeV rather than 2 GeV? That looks like factor 2 on the horizontal scale, but look on the vertical scale. Factor 2 here means 2 or 3 orders of magnitude. And 3 orders of magnitude, we have, say, 10,000 ions in the largest event. So 3 orders of magnitude means we go from 1,000 particles to few. That's very important. Now you see here 2 curves. One which go down here, and the other which have about 1% probability and small pt, but then it goes above, and then describe this intermediate region. Where did that come from? Here is our suggestion where it comes from. So roughly speaking, look at this picture. This is result surface in a schematic way. So the system evolves for some time, and then approximately at constant tau, there is this upper part of result surface, and we usually only calculate contribution from that. And I call it the lead. But there are also, this cup has the sides. And what happened on the sides? So there are also, of course, hydrodynamics, there are some exact solution, which I will not describe. The thing is, now we can go to this picture, and this is from some modern hydro numerical calculations which people use to describe everything. And this is transverse activity as a function of R. R is radial from a center. So these are some different details. For example, let's look at this violin curve. It's at R equals 0, it has 0 radial flow because of symmetry. So it starts like this, and then this part of the curve, linearly rising up to here, is the contribution of this lead. The edge has the maximum, and this is here. But then you find particles which nearly constant transverse activity, which in this case is large, it's 1.4. You may say this is not enough to go to 4 or 5 GeV, but there is, of course, convolution of thermal spectrum and hydrogen. So the interesting thing is that this whole side have about the same transverse activity. And it is this contribution, I return to this, to here, which is very small, percents at small pt. Its total normalization is small. But at large pt, it becomes visible because of this large activity. So I'm saying that, in fact, we are still very modest. Our hydro, people who do hydro for no reason stop around 2 GeV, like we were stopping before. They say that it's numerical, we are out of statistics, etc., etc. In fact, we know where hard region starts and the tail starts. This intermediate region is still not explained. So now I go to perturbations of the big and little bands. We can, people now do this event by event hydro, and it is very complicated initial condition. On each event, there are remnants from each nucleon, so to say, each unit nucleon. And then they start this complicated hydro and go many events till then. I'm saying that because the initial position of this superimposed. Anyway, so both in the Big Bang and the Little Bang collisions, we have some initial perturbation of density and temperature. And in our case, the amplitude of these sounds calculated are of the order of percents. And if you start with a bump, the sound propagates, you have little sphere or circle, and at result time, we have a circle whose size is speed of sound times result time. Speed of sound is of the order of half, result time is about this 12 Fermi, so we have radius of the order of 6 Fermi. And 6 Fermi is also this big circle, which is a fireball itself. So in other words, the size of the circles are the size of the system. In the universe, perturbations are much smaller, 10 minus 1. But the universe is very big. So in this case, the circles on the sky have angular size of about 1 degree. Now you can imagine how many of them are there in the sky. If you put it in harmonics, the harmonics of which there is a maximum, I will show the maximum, the harmonic number is 200, and then it goes to thousands measured. We have only harmonic number of 10 or so. But in principle, the physics is very similar, and we can learn from it. Now, the first thing we suggested with Pilar Stay, my student at the time, was that if it is a sound in linearized PA, then its damping is given by standard theory of sound damping. And it is proportional to viscosity, and because sound imaginary part of dispersion curve is proportional to k squared, it damps as exponent of L squared. And you see that actually this works very well. This is N squared, and this is experimental data for red and left, etc. This is from paper from this. So yes, it is N squared, like it should be for sound. And also here we have 1 over TR. What is TR? T is for microscale and R is for macroscale. Now, if you just measure Vm as a function of centrality, you get this curve showing that elliptic flow is maximal at some mid-centrality. For this reason, small for central and peripheral collision. However, if you estimate the size of the system for each centrality and plot it versus it, you also see that you have this prediction that it is exponent of 1 over r works. So we have preliminary kind of assurance that as a function of harmonic number, as a function of size of the system, this formula describes roughly this harmonics of flow. Now if we go to a particular one bump, placed here, and then wait some time till result, and then calculate result. Surface, this is what you get. This is the speed of result surface plus a sound circle. And if you calculate from this, the single particle spectrum as a function of angle, you see these curves like this. So here are these two horns, as they're called. By the way, see that the amplitude here is smaller, this amplitude here is larger. This is a typical situation which everyone has seen on the beach. When the wave go to shallow water, its amplitude rises. Yes? So the system, if the sound go to the edge of the system, its amplitude rises, and you see these peaks. This is if you use ideal hydro without viscosity, and it is reduced a lot, you see with viscosity. Now, if you calculate two-particle correlation, so the two-particle can either be from one horn or from two different horns. So the correlation function look like this. This peak at delta phi equals 0 is when two particles are on the same horn, and this bump, which is about 1.5 radian up to 2 radian, which is roughly 50-60 degrees between them. This is the angle between the two horns visible in the system. So that was a predicted correlation function, and we get it reported in the morning compartment at 11 at that time, and it was immediately experimentally confirmed in the same meeting. So that was Alice and Atlas, and this is the shape of the correlation function. You see it has direct shape. And also, that was the first time that calculation with zero viscosity, calculation with viscosity, some reasonable viscosity, you really can see difference by eye, and in experiment you see that the shape is correct. Now, this correlation function, as everyone knows, can be decomposed into harmonics. These are ultra-central, most central events. And so harmonics are, you see, the elliptic flow is not enhanced. And in fact, the strongest one, which is this blue, is the further. Now, this was the spectrum which we calculated. These are calculations with different viscosities. Again, we were a little shy on this. And these were the first data which were this Atlas data. And what you see here is this minimum which kind of persisted this calculation. So that was because there is a phase factor, it's called, on top of the bending. What is that? You see, each harmonic is an oscillator, and it oscillates at time. But the oscillator oscillates at some time moment, all energy is potential, and some all energy is